So previously we discussed what makes an integral improper, specifically when one of the bounds is either positive or negative infinity, or we're trying to integrate through a vertical asymptote, specifically if one of the bounds represents an area or location where the function is undefined or there is an undefined value somewhere within the bounds of our integration. And in that conversation, we looked at when improper integrals do something called converging, meaning the value of the integral seems to settle on a finite value, or when the improper integral diverges, specifically the values just continue to increase, that never settles on a specific value. In this video, I want to actually evaluate some improper integrals analytically. In our previous problems, we had just looked at a couple of these integrals and numerically try to get a sense of when these integrals might converge or diverge. But we want to now actually find these improper integrals or evaluate these improper integrals analytically. And as I mentioned earlier, we cannot just plug in infinity into our integral. It doesn't work that way for reasons that I described in the previous video. Since infinity is not a constant, it's not a finite mathematical quantity, we just can't plug it in. So instead, we have to ask ourselves, is there a way that we can observe what's happening to an integral and then see what happens as we increase or one of the values, uh, the behavior of the function as the bounds increase. And we do, we have limits. So all it really is a matter of rewriting our improper integral as the limit of this integral. And instead of having one of the upper bounds or lower bounds, depending on whether or not it's positive or negative infinity, instead of having the bound be infinity, we can really just rewrite this integral as the limit as a approaches infinity, and a being that upper bound. Now, a quick note about notation here. Notice that I am relabeling this as a, and I don't want to use x here because it's just bad math practice to have your bound be the exact variable that we are integrating it with respect to. So we don't want to write this as the limit as x approaches infinity. We're going to label it something else as limit as a approaches infinity here. So we're going to rewrite this integral as the limit as a approaches infinity, a being that upper bound. And we're saying, okay, as that upper bound starts to approach infinity, what is that integral doing? Similarly, if our lower bound were negative infinity and we are integrating from negative infinity to 0, we're going to rewrite that as the limit as a approaches negative infinity. So let's do just a few examples together, and then you can try a few more on your own and check your solutions with the problems that have been uploaded. Okay, so you'll notice that these are the same exact problems that I gave on the other side of the notes, and now we're just doing them analytically. So we've got an integral from 0 to infinity of this function here, and the first step is to rewrite this integral. So we're going to write this as the limit as a approaches infinity of the integral 0 to a. And again, you don't have to use a, but that's just standard practice. So we're going to write this as 1 over 1 plus x squared dx. Oh, and I should clarify. I said you don't have to use a. I meant you can use some other variable, but what you don't want to do is write this as the limit as x approaches infinity. All right, so we're going to go ahead and integrate this. And just full disclosure, for some of these problems, I'm just going to skip some of the steps in regards to integrating just for the sake of time. I'm going to assume that you're well versed in integrating different types of functions at this point. But if we look at this carefully, we should hopefully notice that the integral of 1 over 1 plus x squared is inverse tangent or arctangent. And I know it's been a while for a lot of you since you may have done some integrating. So if that didn't come to you right away, then it's all right. We'll just get back into the swing of things. So, all right, so we got the limit as a approaches infinity of arctangent, and we're going to be evaluating this from 0 to a. Now what we're noticing here is we are taking the limit of this function as a approaches infinity. So I'm going to rewrite this. We're going to take the limit of this function as a approaches infinity. So we're going to write this as the arctangent a minus the arctangent of 0. So all I'm doing right now is I'm evaluating my integral from 0 to a, which means the arctangent of a minus arctangent of 0, and I'm taking the limit of this as a approaches infinity. Well, what is the limit of arctangent of a as a approaches infinity? And you may need to think a little bit about the tangent function here, right? So we're effectively just asking ourselves, at what angle would tangent approach infinity? Well, that would be pi over 2. And the arctangent of 0 is just going to be 0. And so if we're taking the limit of 0, it doesn't matter here because that constant a isn't in our function. We're just saying the arctangent of 0, and that is going to be 0. So we have pi over 2 as our integral. So we see here that this function converges, or this integral converges to a finite value, that finite value here being pi over 2. All right. Okay, let's try another one. Let's go to number 14 on the backside. All right, so we've got another function here that we're integrating. This time we're integrating from negative infinity to 0. So we're going to first rewrite this as a limit statement. The limit as, again, a approaches, and this time negative infinity. So we're going to rewrite our bounds so that a, our lower bound, up to 0 of x times e to the x dx. All right. So this one here, if we were to integrate, again, I'm just going to kind of skipping forward through some of this. If you want to, pause this video and integrate this on your own, but hopefully you get the limit as a approaches negative infinity. And using integration by parts, we would get to x times e to the x minus e to the x from a to 0. Okay? All right, so now that we have our integral, we're going to now evaluate our integral at those bounds. So we're going to say the limit as a approaches negative infinity. And what we're going to do is we're just going to plug in our bounds here, and we're going to rewrite this integral. So we're going to say we've got 0 minus 1, e to the 0 is 1. So we've got 0 minus 1. So this is our integral evaluated at 0. Now let's evaluate that integral at a. So minus a times e to the a minus e to the a. All I've done so far is just evaluate this integral at those bounds. So now we're going to go ahead and, well, before I actually do any limit evaluating here, I notice I've got 0 minus 1, which is negative 1. So I know taking the limit of this isn't really going to affect that negative 1. So I'm going to actually just rewrite this, write that out. So minus, and now we can say minus the limit as a approaches negative infinity of, and I've got a times e to the a minus e to the a. And if we're looking at this here and we've got negative infinity, we're going to result, or we're going to end up in indeterminate form. So if we think about this, how could I rewrite this so that maybe I wouldn't get indeterminate form? And it doesn't happen immediately, but if I actually just rewrite that a times e to the a, that first part of the expression, I can actually just write this as a times e to the negative a. And how is that helpful? Well, if you look at this carefully, that it does now allow me to use L'Hopital's rule. So we're going to say by L'Hopital's rule, we can then say this would become negative 1 minus the limit as a approaches negative infinity of, let's differentiate the numerator, that's just going to be 1. Differentiate the denominator, that's minus e to the negative a minus e to the a. And we're really just doing L'Hopital's for that first part that results in that indeterminate form. And this then gives me negative 1 minus, now let's find the limit. As a approaches negative infinity, it's 1 over negative e to the infinity power. That's just going to give me 0. And similarly up there, minus e to the negative infinity power. Think about what that looks like. Pull up a graph on Desmos if you need to, and that would give me 0 as well. So this integral does indeed converge, and it converges to this finite value, negative 1. Okay. All right, let's do one more problem together, and then you can try a few more on your own. Again, a lot of these integrals involve a number of different types of integrating practices or strategies, and it's a good review for you to try these after a bit of a layoff. All right, let's try number 15 now. So kind of move in here. All right, so for number 15, we're going to be integrating this from 2 to infinity. And again, first step, we're going to rewrite this as a limit statement. The limit as a approaches infinity from 2 to a of this function. A little tedious, but an important step. Now, we're going to go ahead and integrate that. And this one's a little bit easier to integrate here because our function that's being raised to the -4th power is just 2x plus 5. And so that allows me just to apply the power rule and write this as 2x plus 5 cubed, and this evaluated from 2a. Now let's go ahead and evaluate that integral at the bounds. So we've got the limit as a approaches, and you know what, actually, we may just be able to kind of skip to it. We can say, all right, I know that when I plug in infinity, or when I take the limit of this function, excuse me, as a approaches infinity, that's just going to give me 0, right? Because our denominator is getting increasingly large, infinitely large. And then that same integral now evaluated at 2, we can just go ahead and write this. We got 6 times, that's 4 plus 5, that's 9 cubed. And we're going to now flip the signs, and so that's just going to give me 7 times, just punch that into my calculator if you need to, and that's 4374. And so there's that integral there. Okay. All right, so if you need to, watch the video again and follow along, but the integrating part hopefully isn't too bad. But just really understanding that in order for us to evaluate these improper integrals, we need to rewrite these integrals as a limit statement because we cannot just substitute infinity. Instead, we can just evaluate the limit of these functions or these integrals here as a value, in this case, approaches either positive or negative infinity. And making sure that we're just really clean with our notation. That's something that we'll just need to be careful with. So try 16 through 18 and check your solutions in our classroom notes.